Gentlemen, I forgot to tell you I recorded the last session too, and if it's okay by you, I will record this one too. Then I can share this in any way, shape, or form that is possible with you guys. Yeah. Thank you for your consent. We just continue from where we left off the last time. I asked you or said that I was going to ask you what you guys feel like of the, call it the oddities of each section. They will be typically for the Norwegian sector, but I also can quickly mention what is the typical oddities of the different sections around the world. When it comes to conductors, in the Norwegian sector, it's important for the stabilization. We saw that they cement the center pile of a template, but also the conductor. Each conductor would level and stabilize the template. If you want to put a BOP on one side, it's a lot of weight that you rest off. So you would like to have at least 3 conductors cemented before you start to put a conductor in. And what the nice lady mentioned in the previous presentation was a hole opener. You guys have probably seen what a hole opener is, but have you seen the ones they use for conductor drilling? Drilling 36-inch hole, for example. Yeah, so some of you guys have seen them, some may not have seen them. They are like, 17.5-inch bits organized in a triangle, and one in the bottom. So you have a 17.5-inch pilot hole and then 3 bits around, and it's quite a large construction. I can see if I find the picture so you get an idea of the proportions we're talking about. And this is lowered through that hole of the hogs, the hinge over guide loop into the sea. All what you have of possibilities to call it hit that hole when you're floating on a movable rig 300 meters above, approximately, at least in Norway, is the ROV. That would be your eyes, right? And yeah, so you drill for the conductor and you cement it in place. It stabilizes the whole template. Typically little guidance as said, and there are shocks and vibrations even without the boulders. If you hit a boulder, it's quite a shock through the drill pipe going all the way up to the top drive. The top drives, they have a lot of wear and tear in these shallow sections because there's no support, and the string 300 meters is not a lot, and there's no guidance, not enough even weight to kind of straighten the pipe and so on. You get vibrations and shock like a lot, and it goes straight into your top drive. I'm wording myself in the way low weight on bit compared to the surface area of the hole size. So you're drilling, for example, a 26-inch hole or 24-inch hole for either an 18.58-inch casing, which is typical for land-based wells, whereas offshore here in Norway, we typically drill 26-inch hole for 20-inch casing. You can't put a lot of weight on bit, which means that you will end up with low ROP compared to other sections. And the conductor in Norway, 30 to 50 meters long, because what I mentioned the last time. geological time, there has been some compaction of the seabed from icebergs, not icebergs, but glaciers. Sorry, yeah. So the the seabed is very competent. You don't need many joints in order to anchor down the conductor and the well. Whereas in other places, the conductor would be 150 meters long. Yeah, cement to surface, very important to hold the well in place. We'll see a little bit more here and there about that. Inclination less than 1 degree, as what we talked about before. Oops, running quite fast there. Let me see. Drilling for the surface casing, very often without BOP, but what we do is install a diverter. Don't know if you guys know what a diverter is. It's typically something that looks like the annular preventer on a BOP. Basically, it just holds low pressure, not many psi at all, but it you don't really close in the well either, because what may happen in these sections would be the shallow gas or some sort of pressure, and what you do with it, you divert it away. Rigs, they typically have one opening going in the eastward or west, and then the other one in the westward direction, depending on the local weather pattern. Wind in Norway, typically from southwest, you'll see absolutely all rigs orientated so that towards the southwest is the living quarters of the rig, and anything production-wise with hydrocarbons would be on the opposite side of the rig. And that's for the purpose of diverting also, that you guide it so that wind take it away from people and the infrastructure. Yeah. Yeah, go ahead. Both. Both. Well, typically onshore, if you have only one line going just far enough away, and you have what is called a flare pit. That means that you when you are working on a well site, a well pad, you typically excavate the ground so that you have just what I tried to explain in the last session about a glory hole. Basically, that's what you do. You dig a glory hole, or that's where actually the name pit comes from land-based operations, where you just dig in the ground until you have a certain volume, and where the area is sensitive, you put like a tarpaulin plastic to prevent the chemicals from the mud to go into the ground at all. But normally, water-based mud has its, and oil-based for that matter, has in their nature, they're supposed to block and prevent from going into the ground. So in many cases, you don't put anything, because the nature of the mud is not to penetrate the dirt, right? So, but where it's sensitive, we put the tarpaulin, and there you have a pit. Except for a flare pit, there you have ditches, like whatever you dug out from the pit, you make like a ditch. No, sorry, a small yeah, like a heightening, a hill, small. I don't know the word for it. So, but on the back is just a small opening in this in this opposite trench, to put it like that, small hill or bump or whatever, and the diverter line goes in there, and at the end of it, you have a ignition system. so that you can fire it off into the flare pit, and you make sure that there's no entry or access or in and around that area. So it's like a, I don't know what to call it. Anyone have a good word for it when you just make a pile of dirt like this in a long? Yeah. So it's about the height of a man, just to make sure that that nobody enters, really. And when you do cleanup of wells and well testing for that matter, you use the same flare pit to produce the well back until it is ready and steady to produce and deliver into the production system. Especially on some of the onshore structures, also offshore for that matter, there could be quite a distance from the well and up to the producing and separation facilities and so on, and you don't want to put a whole lot of mud or brine or wherever you're having in your well in a mixture with hydrocarbons, gas, whatever. Uh, Typically mud and debris and these things also clog up the production system. Yeah. All right, so water-based mud, we are having returns to sea. So again, chemically, environmentally friendly products. Um, Large volume of cuttings. When you're drilling, and depending on where you are, we talked about CTS, cuttings transport systems. Um, in the northern part of Norway, from Halten and north, out of here, the coast just out of here, we have such a massive effect of the Gulf Stream that it's a natural cuttings transport. You'll see that it comes up and goes quite far away, and it doesn't really land very close to the the well or the templates or any infrastructure whatsoever, and it spreads out. So we don't use CTS much at all. Yeah, and when you're very call it reduced on possibility or to inhibit the mud, typically you'll get problems with stabilizing the formations, because in most cases these are shales in these shallow sections, and they are sometimes a little bit reactive, meaning that you will have bit balling. Sometimes you'll see that when you're drilling, you're not progressing. You pull out and you see that your bit is like the whole drilling BHA is like a Q-tip, basically, and it's all really solid clay. So yeah, low ROP regardless, difficult to maintain mud properties, of course, because the mud goes straight into the sea. Typically to clean the hole, a large hole, small diameter pipe, large BHA, how do you get all the cuttings out? You have to pump as hard as physically possible, right? To get some action. And whatever else you have to help yourself with is would be sweeps. Those would be low viscosity sweeps, high viscosity, heavy, heavy. Some of them heavy in density and so on. Yeah. Cement to surface, very important. The surface casing is a backup for the conductor holding down the well. Yeah, and we see to the bottom right the drawing. This is the land-based typical version. You have the starter head here for the conductor. Very often the starter head. This is the origin of your surface casing. You land. We talked about the PGB in the subsea part in that video, and this is the land-based counterpart, the starter head, we call that very often. Yeah. So and what you can expect on on a surface casing, stability plot, shale formations, pore pressure anomalies may occur, like shallow gas. Fracture formation may occur. That's trouble. You get losses, right? Or unstable. You get like those hourglass shaped holes when you drill them, because the formation is fracture and falls into the well, and you get a lot more cuttings than what you would just from the technical hole size. Yeah, you have a question? Okay. What is important is the second last point in blue down there to the left. In many places around the world, you're drilling through sandstone where the freshwater source of people are. We mentioned that in the last class, and that's definitely an HSC environmental thing. Yeah, we have a question in the back.
Yeah, I mean, the conductor head, is it considered as a part of one head?
Absolutely, absolutely. The conductor sits on it. So it's the conductor sits on it. What we see going down here is the conductor. Now, what you see here, that may confuse you, but uh, that is the pipe that they install with the well pad. I Please forgive me. I simply forgot the name of that one. It was in the previous lecture. It's been a while since I drilled onshore, so but I'll get the name for you. Yeah, and eventually when I get access to Blackboard, I'll upload the presentations, and you will see these videos. And let me propose for you guys, since uh, I said it in the break, the first session in the last lecture was not successful, and the second one was not very high quality, very blurry. So if anybody would like to call me to do the first class all over again, I can do that, so that we can record it and have it available. It will be basically the material science part all over again for anybody. That's just to have it in place. If you find that useful, just let me know. And again, last session I wrote my email on the board. If you guys send me an email, I can actually share with you the presentations now, just as a starting, because I don't have access to Blackboard, as I said right now. But you need to drop me your email and say, hey, kind of interested at least. All right. Extra section. Yeah. When we do things like covering a freshwater source, what we're looking for is the first really competent formation below, and that it has some extent. Meaning that we would like to set the casing shoe that covers the freshwater aquifer into a really good solid formation that we know is going to help us. Let's say that we have a casing shoe extending 30, 40, 50 meters down into a really strong shale below the aquifer. Then we're starting to feel confident that yes, this is a lasting, proper well construction. It's going to be a barrier. Anything that we drill after that casing is not going to interfere with whatever is 50 meters above the casing shoe. And of course, we need a fully successful cement job on that surface casing. I hope you understood what I meant. I'm gonna make a drawing just for the HSC part of it. Surface casing like this, and here we would like to have a competent formation, and we would like to have because here we have some aquifer that people are taking a drinking water from, and we would like to have at least something like 50 meters or maybe even more here of cement, and we cement all the way to surface. So never any risk with regards to people's drinking water or um, any other susceptible water or other sources like this. Could be marshes on the surface, and they sometimes extend under the ground a little bit. There's yeah. Sometimes you even put in an extra section to make these things work fully well. Intermediate casing. In this casing, we install the BOP, and from then on, as drilling engineers, we have to consider open hole design. Said in other words, from that point on, we do calculate kick tolerance. In most casing design software I've seen, kick tolerance is an automatic calculation done in addition. But for most operators, they would ask you to do the kick tolerance calculations, and they would provide you what is called an Excel spreadsheet. And you have to fill in the numbers and you see the kick tolerance. Yeah. As a reminder, looking back, you guys remember kick tolerance? Yeah. What are the kick tolerance regulations basically? You remember? Four? Yes. Yeah. Four. Four. So if this is the intermediate now, okay, but we're going to drill down here. Then we install the BOP, right? And our open hole here needs to have 4 cubic meter kick tolerance. Okay. Now, if do I put this sign or this sign in front of it? More than 4 cubic or less than 4 cubic? What do I put? More. It has to be strong enough, your design, to be able to take at least 4 cubic meters or whatever. Yeah, we disregard whatever is there. We say gas. Worst case. We go worst case and we say for the open hole design, the kick tolerance, minimum 4 cubic meters. There's another requirement too that we operate with in the Norwegian sector. And that's for the next section. Then the limitation is 8 cubic meters. 8. And the simple reason is we may accidentally drill into the reservoir, right? If our measurements are off, if there's a fault that has thrown up the whole reservoir and it's not what it was on the seismics, it couldn't catch it, something like this, then you drill in. And what is the problem with it? The problem is that if you have a long open hole section, right, and then you drill into the reservoir, if you have a casing like this and you have 10 meters open hole and you drill into the reservoir, that's a completely different situation, right? So for a production casing, the one that stops on top of the reservoir, it's a different number. Yeah. In many cases, well, construction-wise, the intermediate casing is backup for the production casing if it's possible. That's something that operators strive to do. If you have gas lift, meaning the production casing contains gas injected from surface through some valve in the tubing, the old style equipment would not qualify as a barrier. meaning that you could not use your tubing as a primary barrier anymore. That means that the production casing only is the primary barrier, and this intermediate casing has to be the secondary. Okay. Yeah, and reactive shales very often. Lately, 17.5-inch sections in the Norwegian sector, they have started to be with oil-based mud. Even though enormous amounts of mud and cuttings, it is collected, everything on top of the rig and shipped onshore for proper handling. All in all, a saving. Why? Because so much trouble with water-based muds drilling these formations. And typically, when we look for where to set the top of cement, we try to cover high-pressure zones. We see in very small here that the casing shoe is approximately into that high pressure curve. So you would cement as high up here as you can. But at the same time, you need to be careful. Why? Because cement is always the highest, the biggest hydraulic impact to the open hole because of the high viscosity it has, and that a successful cement job also has to have some sort of pump velocity. When you are placing it, not when you're putting the cement in the well, but when you are placing it after it has been pumped, you should strive to have some sort of speed on it. Why? Otherwise, it just shrinks out and it gets entangled with mud and it doesn't set properly. So, yeah. So there's always a give and take. Nothing is just an advantage. You always have to sacrifice something, as we see in all drilling designs. Gas tight treads, typically what we see here in the Norwegian sector. Yeah, very often set again in a competent formation to seal off all the troubles and the pressure zones and so on. Yeah, and not cemented into the next casing because of the issues mentioned. Yeah, in all times, this production casing section would be the one that we started with oil-based mud. We displaced out water-based with oil-based, and we started drilling down to the top of the reservoir. This one has 8 cubic meters of kick tolerance. Requirement here in Norway at least, and many operators they ask this anyways, is to have a secondary survey measurement. If you have a systematic error, like you are some portion off all the time, you may not hit your targets, or it may be too late to hit your targets. So that's why you always have an extra surveying tool. Secondary barrier envelope. If the tubing leaks, the casing see the pressure. Yeah, it's designed to withstand all these loads, and that's embedded in governing documentations. And also you see this from NORSOK D10. I guess you already know this. Yeah. Yeah, a casing with some cement plugs here and the seal assembly in pink. We see that this is very similar to the subsea construction. The light wellhead, it's looking so much like the subsea wellhead with the casing hangers just stacked. The only difference being that you just cement, then you pull your running tool, and then you have some mechanic going in there to install the tool with his nose straight into the well, just looking and fixing. Yeah.
Are these valves there for relieving pressure in the different elevator spaces?
These are access to all the annuli, yes. Now, remember that the conductor is cemented to surface, so basically there's nothing going on here, but you still, the truth of it is, when we were drilling onshore, we had one set of valves that were installed during operations, and they saw the returns when we are cementing. Whereas when you're producing, it's a different scope. They are not supposed to see anything coming out, but they will. Any barrier is just a delay. Uh, in time, all annually they produce gas and pressure. So just give it time, and Mother Nature fixes everything, and you'll see pressure coming. Yeah, because nothing is completely static either. Everything moves. It has even if it's slow. Start producing a well. There's small vibrations. The earth moves, and you will have gas migration. It's a topic in itself, gas migration, and that's why we are monitoring all the annually. Subsea, that's not possible. Lately, what you have would be some systems for reading of annulus B, but it's like you read through the casing. It's a magnetic thing and wireless. So on one side, on the tubing side, you read off with a magnetic indicator, and you install it on the outside of the casing when you run it. Yeah. Interesting technology. Used for many different things. Sometimes they actually use these ones to read off live what is going on in the reservoir along the casing. So that's the full extent of that technology. And also another extremely cool one would be the fiber optics that lately came. I should actually show you guys that in Johan Sverdrup field, they have a fiber optic, and it reads every meter of the casing. I'll show you that technology. It's just too cool, and there's a paper from this technology being used in Iceland. They could see the cement coming during the cement job, uh, every single parameter and so on and so forth. So it's operational wise, of course, for production. Um, it has some really quite good advantages. You see what is going on inside the pipe, and also to a degree outside in the formation, and you know the integrity of the well at any point in time by artificial intelligence can read off the signals, if you see what I mean. So it's quite cool. Enough about that. The production casing is extremely important to us. It accommodates the production packer. We need the production packer in place. It needs to be set in an area of the well that is good as a barrier. You guys know well integrity. That's what I understood from the last session. So I'm not going to go more into detail of it, but it's an extremely important casing, and it has its own design criteria standing out from everybody else, simply for a reason: it's backup for the tubing. Yeah. We also have something that we call a drilling liner. If there's a trouble zone, you may just install it to seal off a trouble zone so that you can keep drilling. And as an example, on Gullfaks in the in 2003, we installed what is called an expandable liner to cover a trouble zone. And then we kept drilling, and it's not part of the casing design as per se, or the well infrastructure, other than sealing off this. So it doesn't really hold pressure or take part in the barrier philosophy as per se. We have now arrived at what is going to be the casing design and its process. We will look at what is called a section design pressure. We will look at the acting forces and what we talked about earlier, the load cases, all the different, call it extreme scenarios through the life cycle of a well. We need to know everything. Is it going to be stimulated? Is it going to be fracked? So on and so forth. We are going to take a deep dive into to the strength of tubulars. We are going to look at their collapse capacity, burst, actual, and what is actually only considered as a viable and really interesting matter in the modern design world, triaxial capacity. Yeah. Design analysis, we're going to look into how to understand the curves and results that we're getting when we are using a simulation tool. And finally, what we did is that we made a set of governing documentation for casing design at NTNU, and we're going to look at what are the regulations that you guys will be facing when you are going into the industry. There will be a set of guidelines that this you have to do, this you have to check, this you need to be make sure, so on and so forth. With this set of tools, you will understand also more why and how, and it will basically, point number 5 will support all the other points here. And to put it like that, one way of describing governing documentation, they are a set of accidents and bad experience, right? So you set up these rules and regulations to prevent repeating what the older guys did in older times, right? So yeah. I am not sure that we should embark on casing design now. I see that time has been flying so badly. 5 minutes left now. As said in the last time we lectured on Thursday, we need 2 people to be class contacts for this feedback that goes on. Do we have any volunteers?
Yes.
Very good. I'm gonna need your name and your email, please. And do we have anybody who can support him? Please.
I can be.
Ah, fantastic. Very good. Yeah. So I'm gonna write up my email. You guys send me, and I will send you what I have of the presentation so far. And today's session, I think, will be possible to share with you guys in video form. Sorry about the first one. If anybody of you guys volunteer, that will give me the push to do it all over again, so we get it on video. Otherwise, it's a big chance that it's going to stay with only the PowerPoint part of it. All right. Anything you guys have on your minds, questions, remarks? Yeah. I will ask for the computers that hold the casing design software and prepare that for you guys. And I understand that there is no student assistant in this class for now. That means that holding exercises is slightly challenging. Something is going to be worked out. If you guys want, I can send you the first exercise, and I can also share with you what will be an 80% finished compendium in this class. Everything made the first year, and nothing has progressed since. I'm sorry to say, basically has just been not possible. So sorry about that. But it will support you. It has all these things a little bit more in detail and described in its way, like a like a book normally do. So it could be of help for you guys. So if you drop me an email, you will get whatever you request as much as I can provide. Like that. So just yeah, I think that's it for now. I don't want to talk about casing design. These things are a little bit heavy and we'll forget until the next time anyways. Any few small points that we make up now. And besides, I lectured into your recess. So now you get those 2 minutes back. All right. Thank you.